The steel components were laid across the workbench in Ludwig Vorgrimler's Madrid workshop, like pieces of a mechanical argument waiting to be assembled. It was late spring, 1957, and the afternoon light came through the high windows at an angle that made the machined surfaces gleam. The barrel extension, the bolt carrier, the two small rollers. Each part represented hours of calculation, adjustment, and testing. Vorgrimler was 52 years old, grey-haired and methodical in his movements. His hands carried the precision of someone who had spent decades working with tolerances measured in hundredths of millimeters. On the wall behind him hung technical drawings of the CETME Model C, covered in annotations in German and Spanish, showing cross-sections of the roller-delayed blowback system from multiple angles. He picked up one of the cylindrical rollers, barely larger than a pencil eraser, and examined its surface under the light. These small components were the heart of the entire mechanism. When the rifle was discharged, these rollers would lock into recesses in the barrel extension, holding the bolt closed. As internal pressure pushed the bolt rearward, the rollers would be forced outward along angled surfaces in the bolt carrier, creating a mechanical disadvantage that slowed the opening. The principle was mathematically elegant. Traditional gas-operated equipment diverted combustion gases through a tube to drive a piston, which then unlocked the bolt. The CETME eliminated all of that. No gas port, no piston, no operating rod. Just geometry and mass, carefully balanced. Fewer parts meant fewer failure points, simpler manufacturing, and easier maintenance in field conditions. But achieving that simplicity had required 12 years of refinement. Vorgrimler had first worked on this concept at Mauser in Oberndorf during the final months of the massive global struggle in Europe, developing the Sturmgewehr 45M. When that project ended with the national collapse, he carried the engineering principles across multiple borders, first to France, then to Spain, where the Centro de Estudios Técnicos de Materiales Especiales needed a designer who understood modern automatic systems. The early CETME prototypes, Models A and B, had taught him what worked and what failed. The Model A used a reduced power cartridge that made the roller delay system easier to balance, but defense planners wanted compatibility with international standardization efforts. The Model B attempted to bridge that gap, but suffered extraction problems under the higher pressures of full-power ammunition. The Model C, sitting on his bench, represented the resolution of those problems. It was chambered in 7.622 51 milliliter, the newly standardized cartridge that would dominate Western strategic thinking for the next generation. Making the roller delay system function reliably with this powerful round had required rethinking almost every mechanical relationship in the design. Vorgrimler opened a leather-bound notebook filled with calculations: bolt mass, roller angle, recoil spring constant, barrel length, and pressure curves. Each variable affected the others. The rollers had to delay the bolt opening long enough for pressures to drop safely, but not so long that the action failed to cycle. The mathematics were unforgiving. He assembled the bolt group with practiced efficiency, sliding the rollers into their seats in the carrier, inserting the firing pin, and checking the movement. The mechanism clicked with mechanical precision. Tomorrow, military observers would watch test firings. The hardware had to perform flawlessly, not just mechanically but politically. The nation needed this system to work. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Ludwig Vorgrimler's path to Madrid had been anything but direct. He sat now in the Centro de Estudios Técnicos de Materiales Especiales, the Center for Technical Studies of Special Materials, a bland bureaucratic name for what was essentially the nation's defense development facility. But the route from a technical engineer to a defense contractor had required adapting to circumstances that had nothing to do with engineering and everything to do with history's disruptions. In 1945, Vorgrimler had been part of Mauser's development team at Oberndorf, working under the pressure of a collapsing regime that demanded impossible innovations. The Sturmgewehr 45M project emerged from that desperation, a system that could be manufactured quickly even with degraded industrial capacity. The roller-delayed blowback system suited those constraints. It was simpler than the gas-operated systems of previous models, requiring fewer precision components and less specialized tooling. The prototype functioned, but the timeline didn't. By the time testing began, opposing forces were weeks from Oberndorf. The project dissolved into the chaos of the final surrender, and Vorgrimler, like many technical specialists, faced an uncertain future in a reorganized Europe. He initially relocated to France, where the government was interested in specialized technical expertise. For several years he worked on various hardware projects, but the French had their own established designers and manufacturing traditions. Vorgrimler remained on the periphery, his roller delay system a curious technical footnote rather than a development priority. The opportunity in Spain came through quiet diplomatic channels. The local military, isolated from international alliances and still recovering from internal conflict, needed to modernize its equipment but lacked the indigenous design capability. They needed someone who could work with limited industrial resources, someone whose designs didn't depend on advanced manufacturing infrastructure. Vorgrimler's roller delay system, with its mechanical simplicity, was exactly what the situation demanded. He arrived in Madrid in 1950, bringing with him technical drawings, calculations, and the determined patience of someone who had seen promising work interrupted by forces beyond his control. The CETME organization gave him resources, a team, and the mandate to develop a modern system from first principles. The early work focused on understanding the local manufacturing capabilities. What steels were reliably available? What tolerances could local machine shops achieve consistently? What heat treatment processes were established? Every engineering decision had to account for these realities. There was no point designing a system that required precision tooling the country couldn't produce. The Model A prototype emerged from this assessment, a system chambered for a reduced power 7.92 40mm cartridge that allowed the roller delay system to function with wider tolerances. The reduced power meant lower internal pressures, which meant the mechanical timing of the bolt opening could be less precisely calibrated. It worked reliably, and officials were encouraged. But then international standardization changed the requirements. The alliance was moving toward the 7.62 51mm cartridge as a universal standard. If the nation wanted eventual integration with Western defense structures, their system needed to chamber this ammunition. This wasn't a minor adjustment. It meant completely recalculating the mechanical relationships that made the roller delay system function. The Model B prototype attempted this transition, but encountered significant problems. The more powerful cartridge generated higher internal pressures, which increased friction between the casing and the chamber walls. The bolt, trying to extract the case while pressures were still elevated, would damage the cartridge or jam the action entirely. Standard extraction failed repeatedly during testing. Vorgrimler spent months analyzing the failure modes. The problem wasn't the roller delay timing. That could be adjusted by changing roller angles or bolt mass. The problem was the extraction force required to pull a high-pressure case from the chamber. Traditional systems used primary extraction cam surfaces to break the case free before the bolt moved rearward, but the roller delay system lacked that mechanical advantage. He needed a way to reduce extraction force without adding complexity to the bolt mechanism. The solution required thinking about the problem differently, not as a mechanical extraction challenge, but as a friction reduction problem at the moment of pressure drop. The answer came from an unconventional direction: change the chamber itself. The roller-delayed blowback system functioned on a principle of mechanical disadvantage. and understanding that principle required thinking about forces and geometry simultaneously. Vorgrimler stood before a large technical drawing pinned to the workshop wall, explaining the mechanism to his engineering team gathered around the table. "The bolt never truly locks," he said, pointing to the cross-sectional diagram. "Not in the way a rotating bolt locks by engaging lugs. Instead, we create a delay, a calculated resistance that holds the bolt closed long enough for pressures to drop safely." The drawing showed the bolt assembly in detail. The bolt face, where the cartridge seated, was attached to a smaller mass, the bolt head. Behind it sat the larger bolt carrier. Between them, two cylindrical rollers rested in recesses in the bolt head, positioned to engage with angled surfaces machined into the barrel extension and the bolt carrier. When the system was ready to be triggered, the rollers sat outward, positioned into recesses in the barrel extension. The bolt face was pressed forward against the chamber, the firing pin ready to strike. "At the moment of use," Vorgrimler continued, tracing the sequence with his finger, "internal pressure pushes the bolt face rearward. But the bolt face cannot move independently. The rollers engage the barrel extension, creating a mechanical lock. For the bolt to open, the rollers must be forced inward out of their locking recesses. The geometry created the delay. The rollers sat at the intersection of two angled surfaces, one in the barrel extension, one in the bolt carrier. As the bolt head tried to move rearward, it pushed against the rollers. The rollers, in turn, pushed against both the barrel extension and the bolt carrier. Because of the angles involved, moving the bolt head rearward required moving the much heavier bolt carrier rearward even faster. The mechanical disadvantage ratio, Vorgrimler explained, is determined by the angle of these locking surfaces. A shallow angle creates greater disadvantage, more resistance to opening. A steeper angle creates less. We calculated a ratio of approximately 4.1 for the Model C. For every millimeter the bolt head moves rearward, the bolt carrier must move 4 millimeters. This meant the effective mass resisting the internal pressure wasn't just the bolt head, it was the bolt head plus 4 times the mass of the bolt carrier. The system created inertia through geometry rather than through a mechanical lock. By the time the heavier carrier accelerated enough to allow the rollers to cam inward and release the bolt head, internal pressure had dropped to safe extraction levels. One of the younger engineers asked about timing. "How do we ensure the pressure drops enough before extraction begins?" "Through precise calculation of multiple variables," Vorgrimler replied. He moved to another drawing showing pressure curves over time. Internal pressure peaks almost immediately. Then it drops as the projectile moves down the barrel and the gases expand. We need the bolt to remain closed during this peak pressure phase. The delay time depends on bolt carrier mass, roller angle, recoil spring stiffness, and even the friction coefficients of the moving parts. Change any variable, and the entire system retimes. Too much delay, and the action doesn't cycle reliably. Too little, and we risk a mechanical failure during extraction. The team reviewed his calculations. Pages of equations describing accelerations, forces, and energy transfers. The mathematics were complex, but the mechanical principle was elegant in its directness. No gas ports to erode, no pistons to foul, no operating rods to bend, just rollers, angles, and carefully calculated masses. The beauty of this system, Vorgrimler noted, is also its challenge. A gas-operated system can tolerate significant variation in ammunition power. The gas system self-regulates to some degree. Our roller delay system is more sensitive. The timing is fixed by geometry and mass. If the ammunition pressure curve changes significantly, the timing may no longer be optimal. This sensitivity had complicated the transition from the reduced power cartridge to the full international specification. The 7.62 mm generated substantially higher peak pressures, which accelerated the bolt carrier more violently. Initial testing showed the system would cycle, but extraction reliability was poor. The problem manifested as damaged case rims and extraction failures. Even though the roller delay allowed sufficient pressure drop for safe bolt opening, the friction between the brass case and the chamber wall was too high. The case, expanded by pressure, gripped the chamber walls tightly. The extraction force required exceeded what the simple extractor could reliably provide. "This is where we depart from convention," Vorgrimler said, pulling out a machine chamber from the table. The interior showed distinct longitudinal grooves running the length of the chamber, shallow channels cut into the steel surface. "We float the case on a layer of gas. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The proving ground outside Madrid was austere, a flat expanse of hard-packed earth with target areas at measured intervals and a covered position where technicians could operate the hardware while observers remained protected behind barriers. Vorgrimler stood with the military evaluation team on a May morning in 1957, watching as a technician loaded the CETME Model C for its formal evaluation. The hardware had been through preliminary testing, hundreds of rounds to verify function and identify obvious failures. But this was the official assessment that would determine whether the nation moved forward with production. The observers included not just technical specialists, but manufacturing representatives who needed to assess whether their facilities could produce the system reliably. The technician settled behind the system, checked the chamber, and began a controlled sequence. The distinctive report echoed across the range, sharper than older manual systems, more controlled than heavy machinery. Between bursts, Vorgrimler watched the ejection pattern. Spent cases arced cleanly to the right, landing in a consistent pattern, a good sign that extraction timing was reliable. After 50 rounds, the technician cleared the equipment and brought it to the inspection table. Vorgrimler examined the chamber with a light, looking for any signs of case adhesion or excessive wear. The fluted grooves showed light carbon deposits, but no scoring or damage. He checked several of the ejected cases, looking for marks that would indicate the bolt was opening too early or pulling too hard. "The cases look good," observed Colonel Martinez, the senior evaluator. "The extraction is clean. The fluted chamber is working as calculated," Vorgrimler confirmed. "The gas bleed into the grooves reduces friction just enough to allow smooth extraction without requiring additional mechanical advantage." One of the manufacturing representatives, an older man named Santos, who ran a shop in Barcelona, examined the chamber more closely. "These flutes, they add complexity to the machining process. How precise must they be?" "The depth is critical," Vorgrimler explained. "Too shallow, and they don't reduce friction sufficiently. Too deep, and they weaken the chamber wall. We've specified 0.2 millimeters depth, well within standard tooling capabilities." Santos nodded slowly. "We can maintain that. It requires a specialized tool, but the tolerance is achievable with conventional equipment." The testing continued through the afternoon. They operated the system for sustained periods to assess heating and parts wear. They tested with ammunition from different manufacturers to verify the system tolerated normal variations in powder loads. They deliberately fouled the hardware and continued the test to simulate difficult field conditions. During one sequence, a round failed to fully chamber. The technician immediately stopped and cleared the system. Vorgrimler inspected the cartridge. The projectile was seated slightly deeper than specification, creating an overall length that prevented full chambering. It wasn't a mechanical malfunction, but an ammunition defect. Yet the observers noted that the system had not attempted to activate the improperly seated round. The roller delay system, because it required the bolt to be fully forward before activation was possible, provided an inherent safety mechanism. "The mechanical timing prevents accidental activation," Vorgrimler pointed out. "The rollers must be fully engaged before the cycle can complete. This is an advantage of the geometric approach." Colonel Martinez conferred with his fellow evaluators, reviewing data and inspection results. The system had performed as specified: reliable cycling, consistent accuracy, no mechanical failures. The extraction system, which had plagued earlier prototypes, was now functioning cleanly. The design is sound, Martinez concluded, but we need to verify production consistency. One unit performing well in controlled testing is different from thousands performing reliably in service. Vorgrimler expected this response. The prototype was manufactured using the same processes and tooling we're proposing for production. The critical dimensions, roller angles, chamber fluting, bolt carrier mass, are all achieved with conventional machining. There are no exotic materials or processes that can't be replicated in our facilities. The manufacturing representative nodded. Our preliminary assessment supports that. The design avoids the tolerances that give us problems with other systems. The roller mechanism has fewer critical interface dimensions. What remained was the political decision. Whether the nation would commit to producing a system designed around such an unconventional mechanism. The CETME represented a significant departure from traditional design. Some traditionalists within the military preferred adapting proven designs from other nations rather than betting on an untested approach. But the engineering case was compelling. The roller-delayed system was simpler to manufacture, easier to maintain, and mechanically elegant. And the fluted chamber, that strange, grooved interior that solved the extraction problem, required no additional parts, no adjustment, and no maintenance beyond normal cleaning. As the testing concluded, Vorgrimler packed his notebooks and technical drawings. The system worked. The question was whether the decision-makers would recognize that engineering elegance sometimes came in unfamiliar forms. The final curiosity that made the CETME Model C functional resided in those longitudinal grooves machined into the chamber interior, a feature so unusual that many observers initially questioned whether it was a manufacturing error rather than an intentional design element. Vorgrimler had anticipated this confusion. On the morning after the successful test firings, he gathered the evaluation team in the workshop to explain the principle behind the fluted chamber. He brought with him 2 barrels, one with a conventional smooth chamber, one with the distinctive fluted design, along with several used cases and technical diagrams. The challenge, he began, emerges from basic material behavior under pressure. When a system is activated, the brass case expands outward, conforming to the chamber walls. This expansion is necessary for a proper seal, so gases don't escape rearward. But this same expansion creates friction that resists extraction. He held up a used case from a conventional chamber. Under magnification, the brass showed expansion marks. In many systems, we solve this with a mechanical action that breaks the case free before the bolt begins moving rearward. The initial force can be quite high, but the mechanism provides an advantage. The roller-delayed system lacks this specific surface. The bolt begins moving immediately upon activation, with only the roller geometry creating delay. If we tried to extract against full friction, the mechanism would damage the case rim. He placed the smooth chamber barrel on the table beside the fluted version. We had 3 options. First, add a complex mechanical extraction part, which increases complexity. Second, reduce the internal pressure, which means accepting a less powerful cartridge. Third, reduce the extraction friction itself. The fluted chamber accomplishes the third option through a simple principle. We allow high-pressure gas to enter the space between the case and chamber wall, creating a temporary cushion that reduces friction. The mechanism was counterintuitive. Conventional wisdom suggested any gap in the seal would be dangerous. But Vorgrimler's calculations showed that the shallow grooves, only 0.2 millimeters deep, allowed just enough gas infiltration to float the brass case without compromising the seal. At the moment of activation, he explained, pointing to a technical diagram showing pressure distribution. Gases are at peak pressure. Some of this gas flows into the fluted grooves, creating pressure behind the case wall. This pressure partially counteracts the force, pressing the case outward into the chamber. The result is reduced friction. By the time the bolt begins to open, remember, delayed by the roller geometry, the case has already begun to contract slightly as pressure drops. The gas layer allows it to release cleanly from the chamber wall. Extraction force is reduced by approximately 40%, well within the capability of the simple mechanism. Colonel Martinez studied the fluted chamber carefully. Does this gas infiltration create any safety concerns? Gases escaping toward the operator? The pressure equalizes very quickly, Vorgrimler responded. The gas flows into the grooves, but the case still seals against the raised areas between grooves. The seal is maintained, and by the time the rollers release and the bolt opens, pressures have dropped to safe levels. We've measured this extensively during testing. One of the younger engineers asked about fouling. Won't these grooves collect deposits and eventually affect function? They do accumulate carbon, Vorgrimler acknowledged, but the deposits are soft and easily removed during normal cleaning. We've tested with deliberately fouled chambers. Function remains reliable even with significant buildup. The groove depth provides enough volume that deposits don't prevent the gas floating effect. The elegance of the solution was becoming apparent to the observers. The fluted chamber solved a complex mechanical problem without adding parts, weight, or complexity. It was a geometric solution to a physics problem, the kind of design approach that seemed obvious only after someone proved it worked. This feature, Vorgrimler noted, represents the core principle of the entire CETME design philosophy. We reduce complexity at every opportunity. No gas system, no piston, no operating rod. Instead, we have rollers, angles, masses, and a chamber with grooves. Each element serves a single function with precision. The fluted chamber also explained why the CETME had required so many years of development. The concept seemed simple, but calculating the correct groove depth, pattern, and spacing required understanding the interaction between pressure dynamics, brass expansion behavior, and extraction forces over time. Too little gas infiltration and friction remained high. Too much and the seal could be compromised. Vorgrimler had arrived at the optimal configuration through systematic testing, measuring extraction forces with different groove depths, analyzing cases for signs of excessive gas flow, and testing chambers to verify structural integrity. The final specification represented the convergence point where all requirements were satisfied. This is why the roller-delayed system works reliably with full-power ammunition, he concluded. Not because we force the mechanism to handle higher extraction forces, but because we eliminated the need for high extraction forces entirely. The evaluation team understood now that the CETME was not a conventional system modified with unusual features. It was a systematic rethinking of how mechanisms could be simplified through careful attention to first principles. The fluted chamber was simply the most visible manifestation of that approach. By autumn 1957, the nation had committed to producing the CETME Model C as its standard equipment. The decision validated Ludwig Vorgrimler's 12-year journey from the collapsed workshops of wartime Germany to the proving grounds of Madrid. But the system's influence would extend far beyond Spain's borders, shaping global development for decades through an unexpected connection. In 1956, even before the Model C completed its evaluation, representatives from Heckler & Koch, a newly formed company, had visited CETME to examine the design. The company, founded by former Mauser engineers, was interested in developing a system for the West German forces. They recognized immediately that Vorgrimler's roller-delayed system offered significant advantages for a nation rebuilding its industrial capability. The relationship between CETME and H&K formalized through licensing agreements. H&K would develop their own variant of the roller-delayed system, incorporating modifications for German manufacturing processes and requirements. The result was the G3, a system that retained the fundamental roller delay mechanism and fluted chamber of the CETME, but featured different furniture and sights. The G3 entered service in 1959 and became one of the most successful designs of that era. More than 60 nations adopted it or licensed variants. The roller-delayed system proved adaptable. H&K developed submachine systems, MP5, precision variants, PSG1, and even larger machine configurations. The fundamental principle Vorgrimler had refined in Madrid became the foundation for an entire family of equipment. For Vorgrimler himself, the CETME's success represented vindication of a different kind. The roller delay concept he had first explored under the pressure of the 1940s had finally found its proper context. The system that seemed radical in 1945 was now recognized as a legitimate approach to automatic design. Not an exotic curiosity, but a proven alternative to gas operation. He continued working with CETME through the 1960s, refining the design and developing variants. The Model C spawned improved versions, including those chambered for 5.50 by 6 meter NATO and models for international export. Each iteration carried forward the core principles: mechanical simplicity, geometric timing, and friction reduction through chamber design. The engineering community gradually recognized what made the CETME significant. It wasn't just that the hardware worked, many systems worked. It was that the roller-delayed system represented a fundamentally different approach to managing the forces generated by automatic operation. Traditional designs added complexity to control those forces. Vorgrimler's approach reduced complexity by using geometry to distribute forces across time and mass. The fluted chamber remained a distinguishing feature of roller-delayed equipment. Even as manufacturing technology advanced and designers had more options available, the grooved chamber proved to be the most elegant solution to the extraction challenge. Some later designs experimented with other approaches: coatings, mechanical cams, modified configurations, but the simple fluted chamber, requiring no additional parts and no adjustment, remained the standard. By the time Vorgrimler retired in the early 1970s, the CETME and its G3 descendant had become fixtures in equipment inventories worldwide. The systems served in various regions, from European borders to different continents. The mechanical system he had refined functioned reliably in desert heat, Arctic cold, tropical humidity, and mountain altitudes. The broader significance of the CETME's development lay not in any single technical innovation, but in what it demonstrated about engineering methodology. Vorgrimler had taken a system that existed only as a prototype, and through systematic refinement and adaptation to constraints, transformed it into a practical tool. He had solved the extraction problem not by adding mechanisms, but by changing the chamber. He had made the roller delay system work with powerful cartridges by calculating precise geometric relationships. The system existed because an engineer had been displaced by history's disruptions and found a nation whose needs matched his particular expertise. It worked because constraint had forced creative solutions rather than conventional ones. And it endured because the principles underlying its design, geometric timing, friction reduction, and mechanical simplicity, were fundamentally sound. In Madrid, the original CETME Model C prototypes were eventually preserved in museums, their fluted chambers and roller assemblies becoming artifacts of engineering history. The systems that had once been controversial experiments became recognized examples of successful design philosophy, proof that sometimes the most elegant engineering emerges not from unlimited resources, but from working creatively within constraints. Vorgrimler himself, in his final years, expressed satisfaction not with having created something revolutionary, but with having persisted long enough to see an idea reach its proper form. The roller-delayed system hadn't appeared fully formed. It had evolved through calculation, testing, failure, refinement, and adaptation. That patient, systematic process was itself the engineering accomplishment. The CETME Model C remained in service into the 1980s, eventually replaced by more modern designs. But the roller-delayed principle continued through its descendants, the G3, the MP5 and their variants, equipment still in use globally decades after Vorgrimler's original work. The fluted chamber, that unusual feature that had initially confused observers, became a standard element of roller-delayed design, its function understood and its necessity accepted. The story, finally, was not about innovation for its own sake, but about engineering as a discipline of solving specific problems with available tools. It was about mechanical systems that worked because they were designed to work, not because they followed convention or adopted the latest trends. It was about an engineer who carried an idea across borders and decades until circumstances finally allowed it to succeed. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.